Thanks for joining this presentation. I'm Stephen Diadamo, a PhD student at the Technical University of Munich, and I'll be presenting the joint work with Janis Nutzel about entanglement-enhanced communication networks. This work was accepted into the Ideas category of QCE 2020. In this presentation, I'll cover the following. First, a brief overview of what we mean by communication in quantum networks. Next, I'll outline our proposed phased approach for transforming traditional classical networks into a fully fledged quantum network. From there, I'll discuss a protocol for creating entanglement in the network which occurs when network nodes are sitting idle. Next, we make use of this entanglement to introduce some algorithms for routing when entanglement exists in the network. Finally, I'll review the simulations results we've obtained by simulating the entanglement generation and routing protocols. Communication networks are widely used for transmitting messages in the form of bits between two physically separated points in a network. The Internet, for example, as we know it, is a communication network. Communication networks generally use a layered architecture so that certain tasks are modularized and more easily integrated and replaced. The OSI model is an example of a layered network architecture using 7 layers, as we see in this depiction here. But there are other models which use fewer layers, such as the layered model that we use in the Internet. Quantum networks are much like any other network. There are a collection of nodes or devices in the network that want to communicate with each other. The key difference in a quantum network is that the messages being sent between the nodes are encoded quantumly, such as in photon polarization. Quantum networks are also able to allow two parties in the network to share entanglement with each other. In this picture, we see a simple depiction of a quantum network. Alice wants to send her qubit to Bob, so she puts her qubit into the quantum network routes the qubit, and then it arrives on Bob's side. The motivation for this project is the following. Building large-scale quantum networks will require a lot of effort and resources from many people. We therefore require many strong use cases that will justify building one. Currently, a leading candidate for building quantum networks is to enable quantum key distribution, but this may not be practical enough, especially with the ongoing development of post-quantum cryptography. In the past, we've seen a strong driver of quantum network infrastructure development is being able to increase the network bandwidth. In this work, we started by asking, can we increase network bandwidth using quantum networks? And we found that yes, using the basis of superdense coding, the network bandwidth can, in theory, be doubled. In order to get to a state where superdense coding can be used to increase network bandwidth, we consider taking a classical network and converting it piece by piece into a quantum network, using a series of phases. And at the end of this series, the network will become fully quantum. We consider a phased approach where in each phase, more quantum features become available until the network is fully quantum, with bandwidth improvements at each step of the way. In the first phase, we consider changing the individual links in the network so that they become entanglement enhanced. What this means is that, link by link, we consider replacing the infrastructure to support entanglement generation and quantum communication to perform superdense coding. Here, the physical layer of the network is affected in localized parts of the network. For example, in this picture, we see classical links, and one of them is replaced by a quantum link. The links that are converted to quantum links will require modifications to the link layer so that messages can be encoded quantumly or classically depending on the number of entanglement resources available. On the link layer, we also place the entanglement generation process. Since entanglement generation is at most one hop away in this case, no routing is required and higher layers of the network stack are not required to be modified. The side effect of this is that less processing is needed, leading to lower latencies for entanglement generation. On the network layer, we can modify the routing algorithms to consider the entanglement in the network. When there are paths with stored entanglement, they could potentially be selected as to decrease the transmission time of the messages. Later in this talk, I will give such examples of routing algorithms that use this effect. In the second phase, we consider moving entanglement in the network between the links using entanglement swapping. Entanglement swapping is a multi-party protocol that consumes entanglement units along a path in order for two endpoints of the path to share entanglement at the end of the protocol. For example, if we consider the picture here, if there's entanglement on this link here and this link here, but there's no entanglement on this link here, then the entanglement swapping procedure can be done such that at the end of the procedure, this link uses the entanglement from here to here, and entanglement is existing on this link. In this phase, we consider reshuffling entanglement resources so that high traffic links can be supported with more entanglement when needed. As the technology improves, the swap distance can increase and longer paths can be considered for swapping. For example, in this picture, this path here has a swap distance 1, this one here a swap distance of 2, and here a swap distance of 3. Each of these paths can be used to move entanglement to this link in the middle, but will require more swapping and therefore more robust technologies. Phase 3 of this process is a fully fledged quantum internet. In this phase, all links are quantum and entanglement can be moved to any link in the network. The ability to transmit quantum information anywhere in the network becomes available, and applications using quantum information transmission like cloud quantum computing, can be used. We're now ready to discuss entanglement generation in the network. When links in the network have the ability to generate entanglement, there will need to be protocols in place to handle the creation and transmission of entanglement. Idle nodes in the network, meaning nodes that have no messages to process and are sitting idly, can generate entanglement with their direct connections to be more efficiently used. Here we propose a sliding window-like protocol for generating entanglement frames. A sliding window protocol, in the traditional sense, is a protocol that can be used to reliably and efficiently transmit messages in a communication network. In sliding window protocols, each message is given a number, and a window-sized number of messages is sent from a sender to a receiver. The receiver acknowledges the last message that is received until the full window has been sent, and then the next window is sent. Here we see a picture of such an example. The sender sends 5 messages. In this case, the window size is size 5, and the receiver acknowledges the last message sent, and therefore the next window is sent. We consider a sliding window approach, but for entanglement generation. We consider entanglement frames, which are a collection of entangled qubit pairs. We assume the quantum memory is partitioned such that it can store frames of qubits. Here we make the analogy that one entanglement frame is like one message in the classical case. An entanglement frame consists of n entangled pairs. The protocol begins by generating n entangled pairs and then measuring the first t of them, where t is a number less than n. The sender then stores the remaining n minus t halves and sends the remaining n halves along with the measurement outcomes to a receiver. The receiver waits for n pairs to arrive. If n qubits don't arrive, then the receiver discards the frame and does not send an ACK. Otherwise, the receiver measures the first t of the received qubits and compares them to the measurement outcomes that the sender has sent to compare the entanglement fidelity. If the fidelity is high enough, that is, the measurement outcomes match with high enough ratio, then the frame is accepted and the receiver sends an acknowledgement to the sender. Here, because acknowledgement cannot be retransmitted, we enforce that an acknowledgement is sent from the receiver for each successful frame. In this picture, we show a sequence of 3 different cases of sequences of frames being sent. In the first sequence of transmissions, all frames arrived. In the second, the first frame is not received, and so no ACK is sent from the receiver. The sender waits for some time and eventually times out. That frame which has already been stored is discarded after the timeout. In the third sequence, the frame is received by the receiver, but the acknowledgement is lost. The receiver keeps the frame, but the sender discards their matching frame after the timeout. Here, because we are dealing with unidirectional entanglement, this entanglement frame will never be used. Eventually, the receiver will discard the frame depending on the storage time of the qubits. In order to achieve this protocol, the following hardware requirements are needed. Firstly, we need quantum memories with high enough storage time. We need the non-destructive detection of flying qubits, and flying to solid-state quantum state transfer needs to be possible. All of these technologies are under research, and we cite experimental results in our paper. Because of the unidirectional entanglement resources, we can consider an entanglement rebalancing mechanism so that if there is a lot of traffic in one direction, the entanglement in the other direction that is under less traffic can be used. In this picture, we mark a minimum and maximum threshold in red. Once entanglement falls below the threshold on one end and exceeds the threshold on the other, a protocol can be executed to rebalance the entanglement so that the higher traffic direction can use the lower direction's entanglement. Once entanglement generation is running in the network, the quantity of entanglement on each link will vary with time, and therefore we can consider routing approaches that make use of entanglement in the network. Here we propose a shortest path routing algorithm that first finds the shortest paths between 2 nodes in the network, and then searches the paths for the one where the bottleneck is the largest. By bottleneck, we mean the minimum number of entanglement resources on a link along a path. Another possibility for routing with entanglement is to use multi-path routing based on max flows. Here we can construct a flow graph in the network using the number of entanglement resources available as the basis for setting the capacities on the link. Once the capacities are calculated, a max flow from source to destination is performed, and the flow paths are used for routing. In the second phase, as we mentioned before, we start to introduce supporting high traffic links with entanglement resources from other links in the network using entanglement swapping. In this example, we consider entanglement supplementation with paths with swap distance 1, meaning one entanglement swap needs to be made to supplement a link from another path. Here we see a simple network of 4 nodes. If we consider node I sending a message to node L through node K, then entanglement from the bottom links can be moved to the upper links using one entanglement swap. We write an iterative algorithm to perform this in general. Given a path from source S to destination D and a list of candidate nodes, meaning nodes that are not in the path, check the following. For each link in the route R, and for each candidate K in the list of candidates K, check direct connections into the path and check that there are enough entanglement resources available. And if so, perform an entanglement swap, and update the network. An alternative approach for this is to use a linear program. We start with a set S, which represents the triples of the form Kij, where K is a candidate node with links to both nodes I and J in the route. We define variables x sub Kij to represent the amount of entanglement swapped from link Ki and Kl to Ij, where link Ij is a link in the route. We define the weights W sub Ij as the number of entanglement units on link Ij. With the following three conditions, we aim to maximize the number of entanglement units swapped into the route. The first is that the total amount of entanglement is at most the total entanglement in the network, subtracting the entanglement that exists on the route. The maximum amount of entanglement that can be swapped does not exceed the weights on the links, and there is no overswapping, which we enforce with this third part, where m is the size of a message. In the third condition, when there are two possible swaps to make, the two swaps cannot use more entanglement resources than exists on the link in the middle. For example, in this case, it could be possible that K swaps to either this link or this link, but it can't swap more entanglement than exists in this middle link here. We can generalize the linear program to handle the case when entanglement swapping is done over an arbitrary length. One can refer to our paper for the definitions of the variables and a more in-depth explanation of this linear program, but I'll give a high-level idea for now. Here we aim to maximize a lower bound on the number of entanglement units swapped to the main route from other links in the network. We enforce the following 5 conditions. First, the maximum amount of entanglement that is swapped along a path connecting to a link UV, where UV is in the main path, cannot exceed the minimum number of entanglement resources stored on each link in the alternative path. Here, PUV represents the set of all paths from the nodes U to V. Next, we enforce that for each link outside of the route, swaps for that link is included in multiple swap paths, that we don't overuse the entanglement stored on that link. The third condition is that if an entanglement swap is made along a path, then each link in that path uses the same amount of entanglement. To maximize the smallest amount of entanglement on each link in the route, we have the fourth condition. And lastly, we should not overswap entanglement into the main route. Therefore, we have condition 5, which is limited by the size of the messages. We've simulated the process of entanglement generation, routing, and entanglement swapping using the methods described earlier. Here I'll cover the simulation results. We've simulated 3 different types of graphs, A, B, and C, which I'll show you in a minute. The simulation will run as follows. A source and destination node are selected to transmit and receive n messages of 6 bits each. Once one of the n messages is sent, the source and destination are reselected at random, and a 6-bit message is sent until all n messages are sent. Except in case C, we don't do this. Entanglement is generated after each time step on each unused link, except in case C, where the entanglement is generated with just 50% chance on each link. And we assume that entanglement swapping does not add to transmission or routing time. We measure 2 metrics with this simulation. We measure the network bandwidth, and we measure the number of transmissions it takes to send all n messages. For the first case, we're simulating on a grid network of 16 nodes, as depicted in this photo here. We plot the number of transmissions required to send n messages and then calculate the network bandwidth after the n messages are sent. Here we plot 6 different trends. The green line here and here represents the maximum flow routing using multipath routing when entanglement resources are consumed. The red line behind here represents maximum flow in the classical case, meaning no entanglement resources are used during transmission. The yellow dots behind these represent the shortest path maximum flow routing algorithm when entanglement supplementation is performed over arbitrary distance. The red dots again are using the shortest path maximum flow, but are limited to distance 1 swaps. The black crosses over here represent shortest path maximum flow, but no swapping is done. And finally, the blue plus signs are the shortest path routing, but no entanglement used at all. The results are as follows. Here we can see that the classical multipath maximum flow routing performs the same as the shortest path maximum flow. So here is a maximum flow line behind here, and all 3 of these represent shortest path with the maximum flow using entanglement. The topology of the grid network is such that no swaps are performed, and you can see that all 3 versions of the shortest path maximum routing with swapping and without swapping all perform the same. In the bandwidth, we can see that maximum flow multipath routing performs the best, and the worst case is the shortest path classical. We can also see that the trend of the shortest path maximum flow routing algorithm using entanglement tends to perform as good as maximum flow multipath routing with no entanglement use. In case B, we are dealing with a complete network of 6 nodes. In the complete network, classical max flow multipath routing outperforms shortest path maximum flow even when entanglement supplementation is used in terms of number of transmissions sent. The number of transmissions required for classical maximum flow multipath routing is less than all versions of the shortest path routing, even when entanglement supplementation is performed. In the bandwidth, we see some small effects of entanglement supplementation, but as the number of messages increases, the trends converge to the same bandwidth even without supplementation. An interesting point to note is that when a smaller number of messages is sent, supplementing entanglement from the entire network performs worse than supplementing entanglement from distance 1 swaps. In case C, we are dealing with what we call a wide network. A wide network is a network where the two communicating nodes are these two endpoints here, and there are many routes that are growing outward that connect these two endpoints, with an increasing number of nodes as the network widens. In this case, the classical and quantum maximum flow multipath routing algorithms perform the same, since all of the network nodes are used in this routing approach, and therefore no entanglement is used throughout the simulation. For the shortest path algorithms, we see that with distance 1 entanglement supplementation, there are improvements to the number of transmissions compared to without supplementation, as we see here, and we see further improvements when global swapping is allowed. In terms of bandwidth, we can see a clear separation between allowing entanglement supplementation from distance 1 to global, here and here. And between global and single swap distances, we predict that network bandwidths between these two lines are all achievable. In conclusion, we considered a scheme to increase bandwidth in networks as a driver for quantum network development. We considered schemes for entanglement distribution and routing when the entanglement exists in the network. We've considered schemes to supplement high traffic links with entanglement from other links in the network. And in each proposed phase, there's an increase in network bandwidth, and so immediate gains can be had with each iteration. With this, I conclude the presentation, and I'm happy to take any questions. Thanks.